Right.
All right. Okay. Thanks for coming. This is going to be a weird talk. So if you have specific questions about like this paper or the other papers, please feel free to ask them, because I'm not going into a ton of detail. It's more like high level idea type of stuff with a lot of nice videos. And also I hope people kind of challenge me, because a lot of this is just like wild speculation, and I think it would be nice if we get like a conversation going. So without further, oh no, I'm ruining everything. Will this disappear eventually?
I right.
I think it's most visible in the
No, all right. No, it's not visible
in the recording.
All right. Okay. So as some people might know, unfortunately, I was in this like International Brotherhood of Magicians thing in high school, and so that's why I didn't have any friends and did well in school. So I'm gonna start out the talk with some like introductory motivation stuff. Next. So here's a video. I think maybe some of you have seen it before. Yeah, just. Okay, so did anyone see the ball leave his hand on the final throw? No.
No.
All right, we're gonna try one more. Not this video again. Okay, so focus on like the angle of this cube specifically, and yeah, just pay very close attention to the like orientation of the cube. Fuck, this was the one that I wanted to play in a different video. So how many people think that when the cube reappeared, it was at the exact same position as it was before it disappeared? You can play one more time. Yeah. And how many people think it's like slightly different? Okay, we got a couple slightly different. Artem cheated because I showed him before. Okay, so it's actually off by about like 4 degrees or something, which is like very not so visible. This is a phenomenon that happened. Like you can actually like measure this experimentally, and they call it perceptual momentum. And so there's like a lot of different ways you can measure this, but basically the hypothesis is there's something. If you have a moving object and it disappears, you're going to estimate the position slightly further than it actually was when it disappeared. So we'll go with this. The same presentation. This is the presentation. We'll do one more of these stupid things, and then I'll actually give you stop wasting your time. This one is the one that worked the best for me. So there's going to be these 2 boxes here that are perfectly aligned. And it's helpful if you stare kind of at this background area here. And the background is going to move, and this cube is going to flash on and off. And you're supposed to kind of try to see if this bottom cube looks like it's kind of drifting with the motion side to side. This is like another example of this perceptual momentum idea. So why are we talking about this? I think that there must be some, we'll go into this a bit of detail. This is a geometric deep learning workshop or reading group, and people always talk about like, we need to have stronger priors in our network such that they can generalize better, right? This is kind of one of the main motivations. And so the question is, what is the why do we have these kind of illusions or effects happening for human vision? Some people could say that this is just some sort of like emergent residual phenomenon, right? But there's and that could be the case. But there's a story that John Hopfield tells, actually, he did his on the Lex Friedman podcast, where he's a big proponent of like biological mechanisms for neural networks, and he created the Hopfield network, this model of associative memory, which people have now connected to transformers. But basically, he has a story saying he used to have this old car, and the speedometer didn't work on the car, but every time the car got over like 45 miles an hour, it started shaking like violently. And he's like, yeah, it was a shitty car, but like that shaking was a really good speedometer, right? It always told him exactly when he was going above the speed limit. And so he's saying, even though this is like not the intended effect, it wasn't built that way, you can make use of these kind of phenomena just because of the fact that you are a very smart agent, you have a very powerful function approximator, and he kind of likens this to maybe there's some phenomenon that are happening with these like very complex dynamical systems and neural networks, and they can make use of them to do something interesting. So even if these other illusions are kind of emergent phenomena, maybe this is actually being used for some sort of generalization capabilities. So yeah, I'll go into how these relate a little bit later, and maybe you'll see that a little bit later. Right now, we're going to talk about more boring stuff like equivariance. I skipped these slides. Basically, at the beginning of my PhD, I trained MLP on a data set of MNIST digits, and then I shifted the MNIST digits by like 4 pixels. And the model gets 99% here and like 30% if you shift them just by a tiny bit, right? So what is the difference between these two, and how can we fix this problem? Obviously, maybe not obviously, but this does get fixed if you just instead train a convolutional neural network, right? You have some amount of shift invariances is kind of known. So what are we doing here? We're integrating some form of geometric structure into the actual weights of the network itself, or into the activations and how we're doing the pooling and so forth. So we know that there are some transformations on the input that obey this geometric structure, and we encode this as a prior in our network. How is this done explicitly? Well, in convolution, this is done with some sort of weight sharing over kind of spatial locations, the locations of this translation group. The group equivariant networks and the group convolutional neural networks have extended this really nicely to other transformation groups like rotation. It allows for kind of this generalization like we saw before to these small transformations or to rotation, and kind of all the experiments show this kind of naturally works better on these domains where you need less data, you don't need to observe all these transformations, right? So how can we extend these benefits that we're getting to maybe other sets of transformations which are not as easily understandable in terms of geometric transformations, right? Even though this is the geometric reading group, I'm sorry. So like, for example, say you live in this location and you learn to drive in all different seasons, and then you go on vacation in the summer to these 2 locations, and you can drive on these roads, right? It would make sense naturally that you can automatically kind of drive on those roads in any weather condition. And yet, if we have a convolutional neural network, it's kind of, maybe it could. It's not exactly, you don't get the same equivariance guarantees that you get with something like rotation when you move to more complex transformations like weather or like something like this, right? So how can we extend our guarantees to these settings? So if we think of convolution, like I said, this was done through weight sharing. And some of the earliest work that inspired convolution, arguably in theory, is from neuroscience and this retinotopic mapping of selectivity and kind of the visual cortex. So this is an image of a monkey's primary visual cortex, where they injected this voltage sensitive dye, and they show it this image here, this kind of reversing in contrast. And then when the monkey's neurons fire, it stains the brain cells, and then they cut it out afterwards and they look at it. And the interesting thing is, like, okay, clearly there's like a one-to-one mapping of spatial coordinates here, but also this looks like some sort of like a log polar mapping, right? Because these are closer together and then they get spread out and you have like no longer radial. So this is super interesting. And anyway, the idea that some sort of like shared feature detector is present at all locations, and you have this kind of like translation equivariance. I believe, I think John Lucan said this, was kind of inspiration for convolutional neural networks in the early days. One of the challenges, though, is that in a real neural network, you have a shitload of neurons and a lot of neurons, and they're all kind of independent, right? And so how do you get them to share weights or parameters in some sense, right? And also, how do you get them to organize in this topographic way or retinotopic way when like there's many steps that go from the retina actually to visual cortex, and multiple layers of visual cortex, V1, 2, 3, these different regions all have this retinotopic mapping, which is kind of aligned. So how are they doing this alignment? Some people say it's chemical. It could be learned. It's not really clear, but maybe if we look at kind of other examples, we can kind of see how it slightly could be learned and could also generalize to other transformations, like our main goal is, right? So we're trying to get some inspiration for how we could solve this problem of generalizing equivariance to the larger transformation. So another example of this topographic organization in visual cortex and primary visual cortex is topographic selectivity with respect to the orientation of lines. So if you show a cat an image of like what they do, they like lock a cat's head in and show these images of these like rotating lines, and they measure the selectivity of all of the neurons to which angle is it most responsive to. You see that the neurons kind of are organized such that the ones that are near each other are highly responsive to basically the same angles, and you get this kind of smooth gradient and mapping. And interestingly, also, there's regions they call pinwheels in some animals, not in all animals, where you have all of the orientations in a single location, and you can kind of tile the cortex with these what they call hypercolumns. And this was like Hubel and Riesel's work, like what they got the Nobel Prize for, and they kind of theorized that maybe this is like a general way that the cortex works in general. It's like we have a lot of these things, and they called each one a small machine that looks after all values of a given variable. So interestingly, I think Eric Beckers has said this was part of the reason that he got interested in equivariant neural networks, and also Max is very interested in this. These things are really reminiscent of like what happens in a group equivariant neural network, where you have all of your features, you have one feature, and then you have all of the transformations for that feature kind of like lumped into one capsule or whatever you want to call it, right? And that's the same thing that's happening here. You have like a line detector and all the possible transformations lumped into one area. And then maybe since they're really close to each other, you can do some sort of pooling and gain invariance of that transformation or whatever. But there is some sort of organizational principle that is causing this to happen in the brain. And it's not just the orientation of lines. This is not the presentation I was trying to give. Yeah.
But this is that dimension mean in the
yeah, so cortex is not just two-dimensional, right? If that makes
just the depth of
just the depth of the cortex, and there are multiple layers in the cortex. But so yeah, what we refer to typically as like layers in a deep neural network is usually the different regions of cortex, and they kind of feed into one another. So V1, V2, V4, but there actually are layers to that cortex with a bunch of different neurons that do different things, but I don't think most computational neuroscience people tend to include that part of specificity in their abstractions. So that's kind of abstracted away into like a single neuron, or this is like a group of neurons, right? So we would say this is like some sort of equivariant capsule. So it's not just the orientation of lines, like the body parts themselves are also kind of topographically organized. This is a monkey, see like its fingers are organized and the slice of the brain. There's also, you can find specific places in the human cortex that respond preferentially to places, spaces, bodies. You can see the area, so the area that responds to faces specifically is what got this Nancy Canwisher professor at MIT super famous, because she was the first one to find it when fMRI first started. It's in the same place for almost everyone in the brain. It's like somewhere back down here, which is interesting. But also it's slightly overlapping with the body selective area. So just keep that in mind. I'll show some interesting results later if I don't run out of time. So the question is like, okay, maybe this does something useful. Like, has anyone tried to build a model of this, a statistical model of this that we can use for computation? It turns out, yes, independent subspace analysis can be kind of seen to do something similar to this. I don't know if you remember independent component analysis. The idea is it's a generative model where you have a set of independent latent variables, and then you kind of select one of them and you generate your input. In independent subspace analysis, instead of having independent latent variables, you have groups of latent variables, where each one of those groups, one of these subspaces, they share a common variance, but their means are decorrelated. So when you do something like this, and now each one of these sets of 4 like features is an independent subspace, you see that you get these kind of like correlated features that end up getting learned instead of just like random Gabor filters like you would have with ICA. Now you get like groups of Gabor filters that have some sort of transformation happening between them, but it's not exactly clear what that transformation is, but it is kind of reminiscent of like, okay, maybe there's some sort of like a capsule, an equivariant capsule thing that's being learned here, but the network itself is deciding what gets learned for these transformations just based on what maximizes the likelihood, essentially. So yeah, we need to go a little bit further than this. And also, since these are all, there's no real organization within all of these things, right? These things, like the order of them is arbitrary. It's just a set. So if we want to make the order a little bit less arbitrary and actually have some sort of like a transformation with some topology to it, this is where they kind of did a next step they call the generalization of independent subspace analysis, called Topographic ICA. And so the idea is, instead of sharing your variance between these distinct subspaces, now you kind of share variance in kind of like sliding window overlapping groups, such that nearby components are more independent or more dependent, and far apart components are more independent. So you can see this is the neighborhood of a given variable, and it's correlated with those around it and independent from those that are further away. And when you do this, you end up learning feature detectors or components that have some sort of a topographic structure to them. And so this is like, okay, it kind of looks like we have something that's maybe like a orientation column type of thing here, right? And so this is where we got inspired to think of how can we build something like this into a deep neural network. So specifically, if you want to talk about the generative model that's happening here, like I said, we have our lower level latent variable. So T is a topographic latent variable. And the idea is you want to share variance between sets of these topographic latent variables. And the way you do that is you have a set of independent latent variables, Z1, Z2, which you can call your lower level variables. These are just normally distributed. And then you also have these higher level latent variables, which are also normally distributed, but then you mix them in this way such that you mix them locally and you generate the variances for these variables. So you generate this kind of like mixed variance and then multiply it here. So now these 2 variables, or when you do this multiplication, these 2 variables now have a common variance between them. And you can, do I have it here? No, I don't have it here. And you can extend this to kind of larger groups, and now you see like you have some that are dependent when they're closer and independent when they're further away. So how do we, so all the ICA models have done this with just linear models. It's kind of how you do ICA. You can either solve it analytically or like you do like natural gradient descent with some like really simple rules. We wanted to extend this to deep generative models. And basically we saw that U and Z are both Gaussian. So what if we just learn kind of two independent VAEs, and then we combine these latent variables in this way in the decoder, and then generate a T. It's a kind of the same as doing I don't know what I was trying to say. The same as actually having a topographic prior. It's the same as having this T variable as a prior, but it's like a reparameterization trick for a topographic distribution in a VAE. We have two approximate posteriors. We generate this T variable just by doing this kind of divisive normalization. Pass that into our decoder to generate X, or to calculate the likelihood of X. So yeah, and if you do this and you train it on MNIST, you get kind of, this is the plot we plot for every neuron, the image from the MNIST data set that maximally activates that neuron. And you see these neurons are kind of selective to orientation and class digits. Similarly, if we train this on ImageNet, we see that we get a face region. So we have a specific set of neurons that are selective to faces and selective to objects. And we also can do it for bodies and places. And you see, interestingly, the faces and the bodies are kind of overlapping. Yay. So that's kind of cool. And then yeah, I include this again to say like, hey, look, it's almost the same. Okay. So then we can also do this kind of for more abstract categories. We see like, okay, we see that images that are kind of either animate or inanimate are grouped together, or small or big in real world sense, they're grouped together. So it's kind of learning.
Are these like separate capsules then?
No, this is just the selectivity of these same neurons for different kind of splits of data.
Oh, right.
Because in order to measure the selectivity, you have to present like a dichotomy of two sets of data basically, and measure the relative activation. So yeah, this was work with the master students. I don't know what's happening here. I don't remember what slide this is, so it's probably worthless. Oh yeah, so that's the topographic VAE stuff. If we're not talking about equivariance and we're not talking about through time, that's just like how you generate topographic deep latent variable models. But what if we want to incorporate some sort of transformations into this, right? In that sense, then it makes a little bit more sense to talk about structures. I don't want to say through time, because you can have transformations that are not like through time, but I think for me, the easiest way to think about it, especially in like an embodied biological context, is through time, like, or just some sort of sequence elements, right? It doesn't have to be a time sequence. So kind of the second part of this talk is something I want to talk about, and it'll go into some of the topographic VAE work as well, is instead of how here we were kind of creating a topographic prior over our kind of activations of a regular neural network, some sort of structure in the latent variables of a neural network. What if instead we impose some sort of structure over the dynamics of the network and see if that can instead induce some favorable properties like equivariance, approximate equivariance. And so kind of as inspiration for that, if we look at, no, this is not going to work at all. Creating video, why do you do this to me? If we look at the activities of that, like the local field potential in an actual recording from, I don't know what this animal is, to be honest, it might be a human. some very small portion of cortex, you can see that there is some sort of spatio-temporal organization of activations, right? This recording is obviously very low resolution, but it's not just like random spiking. Like there's spatial dynamics that are at play, and if you do some fancy analysis on this, you can show that there's like some sort of waves interacting. So maybe that's one way that we can think about inspiration for this going forward. But if we want to stick with the way that we built the topographic VAE, and we'll kind of leverage the framework that we have there, where we say, okay, we have an easy way to share variance between variables and data points through this like W matrix that like connects our higher level variables to our lower level variables. How can we use that to induce some sort of structure over time as well? So the idea of like temporal coherence is that if you have a time sequence of highly correlated images over time, you would like your activation to also kind of have some high similarity over time. And specifically, like this neuron over time should be highly correlated with itself. And so you can do this in the topographic VAE framework by now extending your U variables over time and saying that we combine them. So basically we're sharing variance now over time, not just over whatever the spatial dimension was. And we can formulate the T variable that way. But if you think about what this does, what we're saying is that we want these activations to be very similar. Maybe I shouldn't touch it. Very similar to one another over time, which is not really equivariance. That's more of like an invariant representation, right? If you say you don't want your representation to change, even though your input's changing. So instead, maybe we want something that's kind of shifting. So we call it shifting temporal coherence. It kind of seems like a hack, but it turns out it works. So instead of sharing variance over time for a single variable, you share different kind of like shifting subsets of U over time. And so you're saying that your variance kind of shifts through your network over time, and so shifting through a capsule, so forth. You can formulate it this way. And basically when you put all this together, we have this formulation. So we have the Z encoder, the U encoder, and so the U encodes all of the different time steps, not all of them, but like some subset of them. You construct your T variable, and then you get your kind of T activations. And now these can be decoded. And if you decode, you'll decode this Z back. But if instead we roll it forward 10 steps, we can decode 10 steps ahead in whatever the transformation sequence is that is kind of being encoded here. So we have some sort of topographic structure within these capsules. So we come to use what we call the capsule, and it's kind of equivalent to having a single feature, which represents all the different transformations. And so we showed that, I mean, this is like kind of a commutative diagram. We showed that if you take a partial input sequence, you can decode elements that haven't been seen yet for a bunch of different data sets. Furthermore, we showed we get higher likelihoods on these transforming sequences than these non-topographic models. And finally, we measured this equivariance error in terms of what is the difference between the actual activation that the model would have at this time step versus what happens if I take this and I at this time step roll it forward. Like what is the difference between those two? And it's obviously significantly lower in our model where we have imposed the structure.
Sorry, but do you have, I don't understand if this is there a comment? So kind of neural network or
No.
concatenate frames and
Right. So that's it's not I guess, yeah. So one example to the model is all of these images together, but they get fed to the encoder separately. So it's the same encoder Q or approximate posterior for these U variables for each one of these inputs. And so we encode them each separately, and it generates one of these kind of representations, and then similarly for the Z. And then we construct the T variable and decode. So there's no recurrence, it's all, but we are encoding a sequence at once in some sense. Yeah. So the next model, which I like a lot more, is recurrent, and yeah, so maybe I'll try to get to that. So yeah, so this is this idea of like temporal coherence, and really what we were trying to do is just say like, okay, you can think of like structure over time as another form of topographic organization over time, but really it's just we're introducing like spatio-temporal structure in our latent variables instead of just spatial structure. And when we do that, if we organize it in a really clever way by this W matrix, basically how we're doing this sum down here, that's what gives us the structure or the control of what the capsules look like. So yeah, if we think about this though, what's really happening in these capsules as we process this sequence, right? So if you imagine this is one example, and then we shift to the next time step, it's like we take these now, and then the green one is here. What's going to happen in this? Well, according to our equivariance, this would shift by 1, right? All of these shift by 1. So if you watch a video of these capsule activities, as we kind of put in a full input sequence, you're going to have the activations kind of moving around the capsule like this. That looks a lot like a traveling wave of some sort, right? So the idea was like, okay, forget this temporal coherence stuff. Let's think about traveling waves. And so in the neuroscience community recently, there's like a lot of hype about traveling waves across the cortex as well. And they've really measured, you have waves that are evoked by visual stimuli, also kind of like invoked by kind of spontaneous activity. So just sitting there, you have these waves that are going off even if your eyes are closed. But like if you see something like a very sharp contrast image, there will be a wave that expands literally through your cortex, around the cortex of activity, of spiking. So we thought, okay, maybe this is a mechanism that can serve a similar purpose as this structure that we were incorporating here, but without this kind of like really strictly defined temporal coherence where we have to define for every input time step we want it to roll by 1, and we have to choose exactly what the topology is and so forth. So what is a model of a system that exhibits traveling waves and is also kind of used in computational neuroscience? One such system is a network of coupled oscillators. So if you have a network of locally coupled oscillators, which you can describe with the second order differential equation, if you imagine just like a sheet of balls on springs, so the springs are like down here, and you have all these balls, and then you put also springs in between them in like a grid, and you pluck one up, it's going to kind of send these waves out to the other ones, right? So there was one recently, Konstantin Rush, I think it's his name, who built this model called the coupled oscillatory recurrent neural network. This is described by this differential equation, basically just a driven and damped coupled harmonic oscillator. So these are the coupling terms here. So X is your input, or no, X is your hidden state, U is your input. And so U is driving your network at every time step. You have decay terms here for your position and your velocity, but then you also have coupling between your hidden neurons through this W matrix. So this is like between all of the neurons, there's some sort of coupling between them that changes their, or that contributes to driving them. So if you did like, if you want to turn this into a recurrent neural network, you can turn this second order ODE first into a coupled system of 2 first order ODEs by just saying X dot equals V, and then you can discretize each of those ODEs, and you just get these 2 update equations. Now you basically have an RNN with kind of 2 separate hidden states, right? So this is the velocity hidden state, and this is the position hidden state. And so what you do is you just update both of these at each time step. And so this model is, you can imagine it like a set of coupled oscillators, but they're all coupled to each other globally. So they show that this thing works really well for really long time sequences. And that's kind of the benefit of it, because these oscillators have bounded gradient magnitude and hidden state magnitudes over time. So you don't have kind of vanishing gradient problems. And that was the whole point of this paper. But for us, we thought this is cool because, oh, now maybe this thing can exhibit traveling waves if we just constrain these matrices to be kind of locally connected matrices. So what's a locally connected matrix? Just a convolution matrix or a convolution operation. So if we just do convolution on these instead, so basically replace those matrices with convolutional layers, we get this topographic coupled oscillator network. And so we train this thing to do sequence modeling tasks like forward prediction on rotating MNIST or like Hamiltonian dynamics, like bouncing balls or pendulums, stuff like this. And we get traveling waves. So this is rotating MNIST. This is the input, or this is actually the reconstruction. This is our hidden state, and I tried to put a little star here. The reviewers hated this picture. They're like, I don't see the waves. It's very hard to see. The videos are better, but this is the estimated phase of these waves, and this is the estimated velocity of these waves. So you can do some fancy math to actually compute these things. And basically what we show is like before training, there's no waves, this is the velocity, it's all random. After training, you really have this kind of like unidirectionality of waves that are traveling downwards as we train this model to try and kind of predict the next element of this rotating digit sequence. So here are some videos of it. This is videos on rotating MNIST. This is the hidden state. This is another hidden state. This one was trained to try and model just like a harmonic oscillator that's increasing in amplitude over time. And we get this crazy like spiral wave type of thing. Haven't really shown any real benefits to this yet, but it is a model of kind of wave dynamics that is super computationally flexible. So this thing, it matches neural ODEs and Hamiltonian generative networks on these Hamiltonian dynamics prediction problems. So it does just as well. We have less parameters than the fully coupled oscillator network. And we get these cool phenomenon. The coolest things, though, are that if I train this on rotating MNIST and then I measure again kind of the orientation selectivity like we showed for the V1 monkey, we get something that looks kind of similar, right? I have better pictures than that, but we get something that has some sort of localized orientation selectivity. And honestly, I just believe this is because you're forcing the model to decode from hidden states that are highly correlated over time, and you have a wave that's here at one time step and here at the next time step, and then you say you need to decode this and then this. Obviously, those two locations are going to be correlated in terms of what angles they represent. Similarly, if I measure the maximum activating images, we get these kind of the same thing we saw before of like locally correlated orientation and classes for the images that maximally activate those neurons. So yeah, I think, wow, I'm early. Topographic priors learn these structure representations, and you just switch this around. They can be induced either like statistically through these priors or through kind of these structured dynamics. And the structure is flexible to learn kind of arbitrary transformations, it seems like so far, or kind of interesting dynamics. Yep. Cool.
Thanks a lot. Very cool presentation.
Thanks.
And
Oh, Johannes.
no,
Okay. Thanks, Johannes.
I have some questions to start off with, maybe. I was wondering, in this latest or the last model you showed with the traveling wave, if you apply this to rotate MNIST, then you ask it to sort of yes, structure the latent, or you'd like to see a structure of latent space according to this rotation transformation, right? Do you include any like periodicity in the latent space?
Yeah, so we can, I think in this image, I did have circular boundary conditions, so I do
Right.
circular padding.
Yeah.
But it's not strictly necessary. If I remove it, we can still get these waves that happen,
Yeah.
which is kind of surprising, but yeah. What I should say is like the velocity is being driven at every time step by the input still, right? So it always has this driving force coming kind of like out of nowhere.
And then like the video you showed, this is the evolution over these different rotating inputs then.
Right. This is the
Right,
this is
right.
the hidden state, not
Yeah.
the velocity. Yeah.
Okay. I was wondering in the topographic VAEs, have you tried other topologies for your latent space? Because I think the one you showed is kind of tricky.
Yeah. This is like really the simplest possible. Ones as well, but for the MNIST stuff, right? Like the topographic MNIST and the faces, faces and bodies and places and stuff, that was 2D. That was like a 2D grid, but all of the time transformation stuff was all 1D because I didn't know how to do like this like shifting, this like time step shift in anything besides like a 1D, but beside the circle, right? Like how do you decide which direction to shift if you're not on a just like a circle? So that's where this kind of oscillator network helps because I didn't have to define anything. I just say what the grid is and it learns how to use it. But yeah, one interesting thing was I did do some experiments for trying to I don't remember what I did. I did some that were 2D with on like the D sprites data set, like a little like so they use it for disentanglement. It has like squares and parts and stars and stuff, and they're both black and white. If I'm do a 2D topographic organization and train it on those where they're like translating around the image, I can actually get it to learn something that's kind of like convolution, and it is like topically organized. So yeah, but I don't know how to do the shifting. What should I stick over here? Is this better?
Okay, any other questions?
So if you complete it multiple times, do the maps look similar or?
That's a really good question because I said that the humans all have the thing in the same place, right? I've only looked at them with circular boundary conditions, and then there sometimes you can get them to be similar and like cyclically shifted. But I would say most of the time it changes. Yeah, it changes slightly more dramatically, but I'm also like, I'm looking at it at a really coarse grain level, right? I'm just looking at what image maximally activates this neuron, and even between like steps of training, like that'll change fairly drastically. So I think to get a good measure of it, we would, probably need to have some better measure of topographic organization, like maybe looking at covariances or something. But yeah, that would be actually super interesting to look at. Thanks.
neurologies and Hamiltonian neural networks. That's sort of impact of the behavior. I don't know how that. I mean,
Right, you have
it's
some energy,
Yeah. So,
right?
I mean, yes, there's been some. This is the case with your model. Like, what does? How can you interpret this?
These weird waves. So,
It's yeah, exactly. It's because for sure we don't have an but our brain. We don't. This is for sure more similar to what actually happens in our head. But yeah, my question, I guess, is how
yeah, I'm not
what
sure.
interpretability and
I guess the
if used for modeling, for example, almost something how it evolves on according to dynamics. Then
okay, I guess I don't know what you mean by that. Modeling.
just see that.
No.
It
If
could
it,
even be like the topology of the base space.
right,
It's really useful information. You know that the dynamics of the double pendulum is depends on those or
oh, I see what you're saying. Yeah,
what do we interpret? We
pull out of this. I'm not, I mean, I think you can interpret something from looking at the selectivity of neurons as a function of their kind of topographic location, which is kind of what, like the fact that you see faces and bodies near each other is like, okay, these things are, they have similar either like co-occurrence statistics or something like that. But in terms of the dynamics and like for modeling physical systems, I really, yeah, I don't know.
maybe on interesting orders. Infer conservation also symmetries from observations of the dynamics.
Right. Right.
How does this?
I don't know if it, I don't know if it does, to be honest. Yeah, I think, did they do that with the Hamiltonian networks? There was some where they're trying to actually learn the Hamiltonian, the real Hamiltonian, right?
Maybe because they map some very high dimensional space, it's not high dimensional than the actual base space.
Right.
They go from a fixed space to 100 dimensions. Maybe you can find some symmetries, you find some symmetries there, but they don't really do anything about the dynamics of the video. So, but
I think, yeah, I saw a paper, they had a second paper that was like they had some metric that they could run on their learned Hamiltonian to compute if it was somehow equivalent to the true Hamiltonian. And yeah.
And I was also thinking, I read the paper is they force some say ligand structure on the latent space. If you're this was specifically for rigid bodies that rotate, freely rotate. So SO3 is the latent space. And then they learn.
Okay.
They have good performances, very better than state of the art because state space is SO3. I was wondering whether this can also be the case because you just present like you use more bio knowledge instead of yes, topology, since like shape of the latent space where dynamics happen. Make it,
So I think that was our goal, and I think like if I make the topology of this network match the topology of whatever the transformation of the input sequence is, then it works much better.
Yeah.
For example, if I have rotating digits that go all the way around and I have my space is cyclically connected, then it works much better.
yes.
Which makes sense. And so maybe for something like SO3, you could build some sort of 3D topology that's, I don't know. But yeah, I haven't looked too much into the other topologies, but I do think that's super interesting. And honestly, I don't really have a super strong grasp of some of this stuff to be able to tell you how to do it. But if you can tell me how to do it, I'd love it. No, thank you.
Is there any questions from online? In the Zoom?
I see Miltos's face. No, I don't think so.
Can we hear it?
Not.
Perfect.
Yeah, like that on slide, you have like an image of like the latent space, the sunniest thing to run. I think also here in this.
Right, yeah.
Put it on the door, 2D doors.
Right.
But if you look at like a normal 2D latent space for analysts, there's already some kind of topographic organization happening there, right? So to what extent does this method like alter that latent space topographically? Because
Yeah.
for example, here really some
Even in the first like VAE paper, right? Yeah. So I haven't looked at, that would be really interesting to see what the difference in the structure is between the two, if there is some, in terms of like what digits get placed next to each other in some sense, right?
to some extent it's already happening naturally
Right. Yeah, so I guess the difference is that in a normal VAE, the neurons themselves are independent, and sometimes they're supposed to be. And the topographic organization is like within the code of the neurons. So if you change the code a little bit, it's still like overall neurons, but you increase like this one's activation a little bit, then you're going to move to a digit that's similar, right? Whereas in this model, it's like if I have all of my neurons that are laid out in a sheet and I move my activation from here to here, I'm going to get a digit that's similar, right? As opposed to if you took a VAE and you did that and you move your activation from here to here, you're going to get something that's completely different. Because there's, yeah, if you like shift, it's like, it's the difference of, and don't ask me why we want to do it. I mean, I tried to give a lot of motivation and talk, but you're right. I think that was kind of some of the original motivation to even having VAs in the first place, is that you have a smoother latent space that you can do these interpolations in. And in this model, it's kind of just moving that from, I don't know what to call it, like the activation dimension to the spatial dimension, if that makes sense. But it should also still be within the activation dimension to some extent. I haven't measured it though.
Any other questions? Maybe I have one last one. So it's sort of follow up, I guess, to your answer that your model sort of encodes, I guess, the inputs in a location in the latent space, right? Or the location in
like
spatial
domain, like, yeah.
Right.
But it is still distributed in terms of all of the neurons activate to some extent, but it's, you can think of it as like you take your neurons and you sort them according to activation.
I'm wondering in the wave model, how does you showed one image where you basically showed the direction of the wave before training and after training, and then after training you see all the sort of velocities point in the same direction, which corresponds to the rotation transformation, right?
Right.
how do you think are, I don't know if you have any insight into how are the actual inputs in terms of object class, for example, encoded in this one? Is it like periodicity of the waves, or is it?
Yeah, I mean, I have no idea. Yeah, I think it could be. So it's like the orientation selectivity was very strong in this model.
Yeah.
When I showed the oriented gradings, like that map came out super easily. If I try to measure class selectivity, it's not nearly as strong. But there are still groups of neurons, like I showed the picture of the maximum activating images. There are still some groups of neurons, smaller groups, that are highly selective to specific classes. But so my guess is that it's like, this is also something I didn't say, is like a linear layer encoder. So this is not really a deep network at all. It's just linear, and then I have this recurrence. So maybe right now it's just some like distributed representation of lower level features. But I could see it being maybe like, imagine if it's like two classes or something, waves on one half or one class, waves on the other half or another class, right?
Yeah.
Or some other kind of transformation of this. But yeah, the slightly weird and disconcerting thing about it is that for all of the digits, the waves all go the same direction. And for a single model, when you retrain it, you get like a different direction or different frequency. But it seems like it's because we're doing convolution, and so like the recurrent connectivity within a layer kind of is the same at all spatial locations, and it kind of just flows. Yeah.
Cool.
Who knows?
Very cool interview.
You got some videos, yeah. If only you could put videos in a paper, though.
Thank you.
Thank you. No, thank you guys. Thank you so much.
So to wrap up, I think our next session is going to be in 2 weeks. Let me double check the exact date. Yeah, November 25th, and then Artem is going to present his work on Lie group generative. Huh?
Yeah, I don't know what happens housing with like the fixed plans after I agree.
Oh.
So
Maybe
yeah,
we'll reschedule that
I
then.
can speak to someone if someone.
We'll look into
Yeah, we'll
Ivan, who is eager to present his paper to someone.
okay. Well, that
Yeah,
could be an
that's-
option. We'll discuss. That's cool.
Yeah, well,
Okay, and we'll end the session here, and hopefully see each other again in 2 weeks.
or
Also,
maybe-
yeah.